Here's our second type of problem that we'll look at while we're applying equations. I'm not going to go through all of these again, except we'll talk through them as we go through this example problem. But before we do that, what we're looking at here is rate times time equals distance type problems, RTD. A lot of times we abbreviate it. And this is about writing your equations. So this stuff right here works for step 3, or we're using it for step 3 when we want to write some type of equation. And what we have to do in rate times time equals distance problems is we have to figure out which of these 3 things is going on. Sometimes there's a little bit of a variation, but it's usually set up as one of these ways. Sometimes the distances traveled are equal, so your first distance will equal your second distance. That happens if you're going somewhere and then going back, or if they say the distances are the same, but a lot of times you'll see as this person goes to the park and then they return, or actually in the example we'll look, the 2 people are starting at the same place and going to the same place, so the distances would be equal. The second type of situation is the distances add up to equal a total distance. This is usually when there's a couple different examples, but one of them would be if 2 people are leaving 2 different cities and they meet somewhere along the way. So the first person's distance plus the second person's distance will equal their total distance traveled. So let me actually just show you that real quick here. So let's say there's 2 people traveling 2 different cities. Oh, that was supposed to be a straight line. And if they're traveling and they meet here, this first person's distance, so we put a d sub 1, plus the other person's distance, because they're coming this direction, will actually equal the entire distance. And then the last one is one distance. Is it a given amount more than the other distance? This might be if someone leaves earlier and travels further, or something like that, where it has an extra distance involved. Let me go back to the second one, because I could have also said maybe 2 people start at this city and one goes east and one goes west. So this person's distance, I just said that backwards, one goes west and one goes east. D sub 1 plus D sub 2 could equal the whole thing. So let's take a look at this example here. It says example 2 because we worked with one equation already. So Ted and Jeff are leaving their house. They're at the same house. They plan to meet at a campground at noon. Well, that's important. That's a time, so that's 12 o'clock. Sometimes we look at that. That's a word, but it's also a number because it has to do with time. Ted leaves at 9, and Jeff leaves at 9:30. Jeff drives an average of 8 miles per hour faster than Ted. Should be than Ted. Find the speed of each if they both arrive on time. So they're supposed to meet at noon. They both get there at noon. So this is definitely rate times time equals distance, because they're traveling at a certain rate. They're going somewhere. So we've identified that it's a rate times time equals distance problem. We want to assign an unknown. So what is the unknown? It says find the speed of each. So once again, we have 2 unknowns. We want to find the speed of each. So we could call his rate could be t, and Jeff's rate could be j, or something like that. But we don't really want 2 variables. So let's look at this. Jeff drives an average of 8 miles per hour faster than Ted. Up here, we want to assign a variable to the main unknown, the one that the others are being compared to. So Jeff drives an average of 8 miles per hour faster than Ted. So we're comparing it to Ted's speed. So let's let R equal Ted's speed, or rate, so we did that. And now let's come down to the next part. Plan. Describe any other unknown in terms of the variable you've chosen. Well, if R is Ted's rate, Jeff drives an average of 8 miles per hour faster than Ted. So what is Jeff's rate going to be? Well, his is 8 miles an hour faster than Ted. So if Ted's is R, Jeff's is R plus 8. He's going 8 miles an hour faster. All right, so we have that. So what else do we have here? We know we have a distance problem here, and this does fit this right here. So we can make some tables here, or a table might be the easiest. And this is how we can do this. We have a rate, a time, and a distance. So we know that rate times time is equal to distance, and we can do this for Jeff, and we can do this for Ted. So what is Jeff's rate? Jeff's rate is this R plus 8. Some of you might have put Ted on top, that's fine. So R plus 8. Ted's rate is R. Time, Jeff's time. Let's see here. Ted leaves at 9, and Jeff's leaves at 9:30. Well, we have a starting time there for these guys, and they both arrive on time, which is noon, which is 12. So Jeff's time, he goes from 9:30 to 12. So 9:30 to 10 is half an hour, and then 10 to 12 is 2 hours. So this is he goes 2.5 hours, Jeff does. So I'm going to just put that as 2.5. Ted's time, well, he left at 9. He gets there on time at noon, so he travels for 3 hours. Well, we know that rate times time is equal to distance. So rate times time equals distance. So in this distance, try to squeeze this in here. This is our 2.5 times our R plus 8. Because that's rate times time. And here, rate times time, we'll just put 3R. So these are the two distances, Jeff's distance and Ted's distance. Now, we have to look here. How are the distances related? Are the distances equal? Do they add up to equal a total known distance? Or is one distance a little bit more than another? And in this case, they're both leaving their house, and they meet at the campground, so their distances are equal. So we would say Ted's distance is equal to Jeff's distance. So that's an equation that we have. Well, what do we know about their distances? Ted's distance is right here. His was 3R, because rate times time equals distance, so this is 3R, equals Jeff's distance. Well, Jeff's distance is right here, 2.5 times R plus 8. And now, we did a lot of work, seemed hard, but now we're at least down to an easy equation to solve. We got 3R equals, we can distribute here, we got 2.5R equals 2 plus so plus 2.5R, 2.5 times 8 is 20. We can subtract 2.5R from both sides. Well, we have 3 minus 2.5, well that's 0.5. We have 0.5R is equal to 20. Divide both sides by 0.5. So R equals 20 divided by 0.5. 20 divided by 4.5. Be careful with this. You're dividing 20 into halves, so how many halves would you have? You would have 40. And this is in miles per hour. So we found R was 40. We solved something, but make sure you check to see if you answered the question. It said find the speed of each. We found R. What did R stand for? Well, that stood for Ted's rate. So this is Ted's rate. We need to find Jeff's rate, or speed. Well, we know Jeff's was Ted's plus 8. Jeff drove a bit faster, so we have 40 plus 8 is 48 miles per hour. And so there are the answers to this question. We found the speeds of each. In this case, we use the two distances were equal. It will not always be that case, so make sure you think through the problem to see what situation it fits here.